Hello, good morning, and welcome to chapter 5. This chapter is entitled, you can't see that on this first slide, it's entitled Orthogonal Transformations or Linear Isometries. Okay, so we're going to talk about something that is called isometry. Um, let's have a look at what we have here. The term isometric comes from the Greek and it means equal measure. So, what I want to show you here, and maybe the gamers around you will have an idea of what we're talking about. We're talking about isometric projection. And what is that? It's just a method for representing three-dimensional objects into two dimensions. So that was very popular in the 80s and the 90s for video games because it was quite simple to compute, and you could use the restraints resources of computing resources of that time to give a nice 3D rendering ID. Okay, and well, it's not isometric, but the isometric, it just means that you had that specific kind of projection where the three axes had the same rotation and you would keep the same distance along all these three axes. All right, so, well, if you want to learn more about that, you can Google it, maybe begin with the Wikipedia page. I've got a small excerpt of that same page on the next slide. So, what are we talking about? So, as I said, it's the specific kind of projection where you see among the three axes you've got the same angle. And how do you do that? So you begin with something that has three dimensions, an object, an item in R3, that one, and you want to do two rotations. These are the isometries that we're going to study in that chapter. Well, some of the isometries we're going to study in that chapter, and probably you already know about rotation matrices. Maybe you studied that with Mr. Biles, or in mechanics, or in some other topics. All right. So this is an example of isometry, but then of course we lose this idea of preserving length because next thing is doing the projection. So here you see a very simple projection matrix, the one where you only keep the first two values of the project of the three-dimensional items. Okay, you just keep the XY component of your XYZ. All right, and that's a very, very simple projection matrix, and I hope you all understand how well this matrix is doing in order to do this projection. Right. Um, okay, so let's see for that chapter. As I said, it's called orthogonal transformation or linear isometries. So we're dealing with automorphism. So I remind you, it's just isomorphism, meaning bijections, from one linear space into itself. And in our case, so our linear space is going to be assumed to be Euclidean, which means it's just a nice space where you will have defined a good inner product that makes it a pre-Hilbertian space, and if it's finite dimensional, then it's called Euclidean. And as I probably already mentioned, it just means that it makes the spaces that are the easiest to work with because it really works with a geometry that is very intuitive, very similar to what you can experiment every day in your own three-dimensional space. Okay, and so those isometries, as we said, are going to be linear transformations that preserve the length, as length being obtained from the Euclidean distance that you got from the fact that you've got a nice inner product. Okay, so let's begin with a few refreshers and just to settle the frame we're going to work with. So we have our Euclidean space E, and we assume that we've got an orthonormal basis. and you know what it means. Each vector has norm 1 and they are orthogonal 2 by 2 with respect to the defined inner product. So just very quick calculations in this orthonormal basis, which was the previous chapter, okay? But I want it to be very clear for everyone, right? So any x that belongs to that space has some coordinates. So your space, let's say, has dimension n. We know it has finite dimension. Let's settle that it has dimension n. And the coordinates of x in the basis B, they are given by that scalar product. Okay? Xj, the jth component of the vector x, is going to be obtained by doing the so let me take maybe a big letter to indicate the whole vector, the inner product between x and the jth element of the basis, right? So let's just expand that using the usual property of the inner product, and you must be very good at that after last week's homework. So I'm doing the sum of xj sorry, let me take another index, xk ek with ej, right, for k is equal to 1 to n, and you know how to expand that by linearity. That's just going to be the sum of xk, as all these xk belong to r, or real numbers, times the scalar product between ek and aj, for k is equal to 1 to n. And you know that as this is an orthonormal basis, this is equal to 0 if k is different from j, and 1 otherwise if k is equal to j. And we have a very nice notation for this, and maybe you've already seen that in some other class. This is the delta of well, it was k and j, and that is the Kronecker symbol, right? Kronecker symbol. Delta, which just says it's the integer that is 1 if the two indices are the same, and 0 otherwise. Okay, all right. And so let's go back to our calculations. So in that above sum, we're going to keep only it's non-zero and in particular equal to 1 when k is equal to j. So we just get the xj component, right? So and so xj is obtained as the inner product between x and the jth element of the basis, and also we can write that the fact that x has those components in the basis e1 to en, it just means that x is equal to x1 times e1 plus x2 times e2 plus blah 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 xn times en, that I've just expressed the fact that it was the components of x in that basis, and using the above notations, well, the above calculations, I know that it's just going to be the sum of x with j times ej. J is equal to 1 to n. Okay, well, or k, whatever the index you want to use. This is what we've got here. Okay, and now when you've got two items, x and y, maybe this is some of the calculations you have to be able to redo, to how to expand, sorry, how to expand that part to get those expressions. All right, so pause the video and be sure you know how to redo to obtain these calculations. Okay. assuming you've paused the video and done those calculations. Well, another way to write that is using the notation of the dot product that you've already seen. So that's x dot y or y dot x, using the dot product notation, and you can express that using the transpose notation of the matrices. Okay, okay, what next in particular? We have that the norm of x is given by the scalar product of x with itself. And okay, and next, given an endomorphism U on E, its matrix representation in basis B, in that basis B is a matrix with the coefficients given by, so the coefficients on the row I, column J is going to be the scalar product of EI with U of EJ. Why? Simply because you remember that if you want to make the matrix A in that basis, you will want to take U of E1, U of E2, etc., U of En. So each column is going to be the image by this map, this endomorphism of each column vector. So that we get E1, E2, blah blah, En. Okay. So so that's U of E1 here, we get the component among E1 of U of E1, and so you know that you get that component by, so U of E1, you want the first component in that basis of U of E1, so you have to take its scalar product with E1, all right? According to what we saw above. Second coefficient here, I want the second component of U of E1, it's going to be the scalar product of U of E1 with E2, okay, and so on. So that you get this formula for the matrix component, right? And using the previous notations, you can also get that kind of expansion if you are doing the scalar product of U of x. You have applied transformation U to x and take the scalar product of this one with y. Of course, U of x is given by U of x is given by matrix A times X, okay? That's the whole point of getting a matrix representation of a linear map. You can just write its action on any item of the space as the product of the matrix times this item, okay? And of course, you can rewrite that using the transpose notation, and just this is what you get. All right. Next comes a reminder about hyperplanes. We've talked about hyperplanes, well, briefly in tutorial. It's just the idea that an hyperplane is, if you're in dimension n, an hyperplane is going to be any n-1 dimensional linear subspace, okay? And what we can show that is that if you've got, okay, H and n-1 dimensional subspace of a space E of dimension n, its orthogonal complement H orthogonal is going to be spanned. Well, I just need one vector to span the remaining dimension that I'm missing. So by the span of A, and you can get the, we can show that there's an equivalence between that and this, and you get then the idea of the orthogonal, the Cartesian equation of the hyperplane is just going to be all the x's that are orthogonal to that vector A, right, which is written like this, right? So if A is spanning the orthogonal to H, then it's the equation of h. You can get an equation of h by saying that it's this one.